What is the graviton? Here, let's see if I can get it. Uh, I'll start with this. I'll say that most humans are mathematicians. I'd say at least 95% of humans on Earth are mathematicians, and only about 5% are physicists. They think in physical terms. They are rational people. The majority of people think in terms of spirits, and those people who in the past used to think in terms of spirits, ghosts, gods, angels, that sort of thing, they moved into something new, which is, concepts, abstract concepts. They believe in fields, in mass, in energy, and they move these things around thinking they're things. And that makes a difference, which is what I was talking about earlier when I started today, the introduction. Okay, and here it is, more or less. 95% of humanity, they're mathematicians. Traditional mathematicians, they work with spirits, angels, gods. The modern mathematicians, they move concepts around. They think concepts cause things to happen, and so all the physical interpretations are mediated by abstract mathematical concepts. On the other hand, 5% of humanity are physicists, and physicists are people who believe or who have the sense or theorize that Mother Nature does not work with concepts or with spirits, that there are objects there that we cannot see or touch. And an object that we cannot see or touch is not the same thing as a concept. An object that we cannot see or touch is not the same as a spirit or a god. Okay? So mathematicians essentially believe in black magic, whereas the physicists think that Mother Nature is simply messing around with us. She's fooling us. She's doing a magic trick. She's not showing you what's in that invisible world of hers. That's all that there is. But there had better be something in there. Okay? We would like to think that Mother Nature looks something like this. Okay? Cute little girl. Okay? That's nice, naive. This is Mother Nature. She loves us. Okay? Mathematicians have a different version. They think that Mother Nature does black magic. She's a mean old witch. Okay, so I don't know, you might want to consider which side you're on. Do you believe that Mother Nature is fooling us, or does she actually do black magic? And here, let me give you an example. Okay, here it is. Okay? You go to the show, and there's a magician on stage, and you see this. Okay, guy moves his magic wand, and he makes a rabbit disappear. Okay, or appear. I'm sorry. There he is. Disappear. Moves it around. Okay, wand around, and the rabbit appears. Okay, simple. Okay, a lot of you saw tricks similar to this one, right? And so you ask the mathematician next to you, how did he do that? And the guy says, well, he made it appear from the void. They actually believe that the rabbit was made from nothing. You have the quantum mechanics, mechanicers, right? And they believe, or they theorize, right, that particles come in from the void. You have the general relativists, and they believe that matter, the universe, so to speak, right? In fact, space and matter, right, had a beginning. There was a start. It came from nothing, which is what space is, nothing. But they say space came from nothing too, I guess, right? Because space is something in their view. So space, the something space, as well as the something matter, both space and matter, they came from absolutely nothing. And they have no problem believing in this, in theorizing like this. And they'll tell you this in your face. And so, yeah, they believe that the rabbit came out of nothing. And they'll tell you, yeah, and they have no problem believing this. They have no problem theorizing like this. Now, they don't lose any sleep over this. And so, yeah, it kind of worries you because you say, how can it possibly be that these people went to college 10 years and more, they're professionals, and they actually theorize, they propose the physical interpretations include the appearance of something out of nothing. Matter out of space, not even space, I can't even say space because even space came out of space, or better yet to say space is a something that came out of nothing, whatever nothing is. Because they never define nothing, they never define space. They just say it's infinite, it's made out of particles, and there's energy in there, and blah, blah, blah. They fix the problem that way. Okay, but this is what they believe. That's what a mathematician believes, and 95% of humanity are mathematicians, and only about 5% are rational humans. We call them physicists. Okay, and last week I talked about this, the fact that you have the Higgs. What is the Higgs? Well, you can think of it as a bunch of fish going through the ocean. And the Higgs is a particle of mass that goes through a field known as the Higgs field, the ocean in this case, right? And some fish move easier through this ocean, and some fish take, or have a hard time getting through there. Those that have a hard time, they weigh a lot, okay? And those that are thin, I guess, or have less volume or whatever, weigh less, they move easier through the river or through the ocean, and because of that, they have less mass. This is the notion they have. So mass is a question of interaction, according to the Higgs version, right? And you could say that the Higgs is the opposite of the graviton, because whereas the graviton causes gravity, the Higgs kind of opposes gravity. It has this inertia. It scrapes its shoulder or its elbow against this ocean, right? And so we have, on the one hand, you have the gravitons. I guess you could say the field of gravitons, the particles that form this ocean, and you have the fish moving against the ocean, and it interacts with it. And because of that interaction, we have the particle of mass and the particle of gravity, the graviton. I guess that's the best way I can put it, because they never really visualize it. It's all math. And we're trying to visualize it because we're trying to figure out how this universe works. How does gravity work, especially at the quantum level? Okay, so that's what we're trying to explain here. We're trying to visualize it. We're trying to imagine what these people are talking about, trying to make a movie of it in our mind, right? Okay, what's the problem with that? Well, with the so-called Higgs. Well, it's a particle of mass, but mass is defined as the quantity of matter, or a measure of the quantity of matter. So we're talking about quantity of matter. We're talking about number of particles. We're talking about counting marbles. Okay, we're saying in this case we have 12 marbles. That's the mass of that object that you see there. It's a 12 marble object. Then we all understand. We say, okay, 12 marbles here, 20 over there, 100 over there. We understand that. Weight, on the other hand, is a measurement. It's not counting. It's got to do with measuring. Okay, and what you're measuring is a resistance of some kind, an interaction. So the particle of mass, known as the Higgs, is actually a particle of weight, because it's defined, the Higgs is defined as an interaction of the Higgs particle with a field. There's some kind of interaction there, and there's resistance, there's some kind of, I guess, friction, whatever you want to call it. And because of that, the particle has mass, and that mass somehow is transferred to other particles. If you can try to visualize that. They do it mathematically. We don't care about that. We want to know how it works in real life. And of course, they cannot visualize that. But my point here is that the Higgs is, like I said the other day, it's a particle of weight, because it has to do with interaction. It doesn't have to do with counting, which is what mass is defined as. Okay? And of course, they had to define mass in different ways to incorporate weight into the definition of mass. That's what I'm saying. Mass and weight are exactly the same until the mathematicians are able to separate one from the other through a definition, first of all, right? And then, they determine mass by weighing. So right now, we can't tell the difference. They say, look, if you take the Legrand kilo, that used to be the standard of mass in France, right? If we take Legrand all the way to the moon, it's going to weigh less. And we say the weight changed, but not the mass. But the mass changed because what we're going to do on the moon is weigh it. We don't know how many atoms or hydrogen atoms, unit of mass, the Grand Kilo had here on Earth, and we don't count them. We just took and weighed it. And so, it weighs differently. That means that the mass also changed because we determine mass by weighing. So we haven't learned much with the difference between mass and weight. Okay, so here we have a simple trick that I sometimes do here. Here I have a spoon, okay, and I'm going to drop it, okay. In fact, I didn't drop it. What I did was just let go of it, okay. I didn't push it downwards, and somehow it falls to the ground. It doesn't fall to the ceiling. How do you do it with gravitons, which is the quantum proposal? Well, you let go of it, and it goes down. So you think that the only way that can be done is something pushing it from above. I don't think you could have particles pulling it from below. How do you pull with particles? It's got to be a push mechanism with particles. You know, you can't pull with particles, no matter how you say it. Now you can have this shadow effect like Lesage and so on, no problem. But it's always going to be a push of some kind. Okay, so we're talking about push gravity when you're talking about gravitons. Okay, and here it is, more or less illustrated. Okay, you have the green pixels, as our science critic suggested once. You have all these particles pushing the spoon downwards. We can all understand that. Okay, it's got a lot of problems because you say, why are the particles directed downwards? Okay, why aren't they upwards? Why aren't they sideways? What happens to those particles? But we can understand the mechanism. If someone says, look, the spoon came down because particles pushed it down. Okay, we understand the mechanism. No problem whatsoever. The problem now is that that's the quantum version, assuming. There are other versions, but I'm just going with one of them, which is gravitons pushing it downwards. Okay. Here's the general relativity version, which does not include particles, which does not include force, in fact. Okay. Here's the general relativity version. Okay. You have a spoon, and it just is pulled down, I guess, because the canvas, the space-time canvas, so-called four-dimensional space-time canvas, goes downwards. Okay. So either it creates a hole and the spoon just falls in that hole, or the spoon itself is pushing it down. Who knows? But the point is, this would be something similar to this would be what the general relativistic version would be. And so how do you reconcile these two versions? You have on the one hand the particles pushing it down, and here you have the general relativity pulling down, where the canvas falls underneath the feet of the of the spoon. You cannot reconcile these two versions. So even if they get all the math together and they figure out, how gravity works in the quantum world, and they figure out the gravity, the graviton, what it is, a bunch of particles pushing it down, or transferring negative momentum, or any of that, that mechanism is irreconcilable with what we have in general relativity, which is the space-time canvas mechanism, which is why Einstein became a hero in 1919 when Mr. Arthur Eddington proved that Einstein's theory was correct. So we have these two mechanisms, and they're different. They cannot be reconciled, and so we have a problem, because it means that even if these people who are researching, in the case of general relativity and in the case of quantum, they're researching gravity, they're never going to put the quantum world equal to the general relativistic world. It cannot be reconciled. Okay, and so what happens here? We have the middle version, the one that has been growing maybe in the last 40 years. They're trying to get away from the particle, and they're trying to get away from the canvas, so to speak. And the way they get away from that is they made ever more popular, stronger, the theory of fields. Okay, so they're all regions, not only the general relativists and the quantum mechanics, but also the string theorists. They're all working with fields. Why? Because the field is a very, you could say, accommodating entity. On the one hand, they say the local vibration of a field is a particle. But at the same time, the field, what is a field? Well, it extends all the way to the edges of space-time. So you have the best of both worlds. The field represents two things. The localized vibration, which is a particle, point or whatever you want to call that, and also it extends all the way to the edge of space-time. So it's got the discrete and the extended all in one. That's why they love the field. So the field, you can hear all these people these days talk about field, quantum field theory. It's general relativity, it's a field theory also. So everything is a field now. Okay? And so here's the vibration, local vibration of the field. Okay, I showed it for the Higgs the other day. I'm going to show it also for the graviton, because there's no difference. They're gonna say that L particles are just local vibrations of the field, and so there you have a graviton. That's what a graviton looks like. You always wanted to know. There you have it. That's what a graviton looks like. Don't look for it in the standard model of quantum mechanics. You won't find it there. They don't have the G for graviton. That's why it's not in the standard model. But here you see it. This place always illustrates everything. We illustrated the graviton for you. That's what it looks like. Okay, and here's what a bunch of gravitons look like. Okay, more or less like that. You can see all the you see the field, which is the whole thing, the whole shebang, and then you also see the local vibrations of each field or regions of the field. And so we have both particle and we have also an extended field, all in one shot. Okay, so this is what they love. They love this thing called field, because it gives them the best of both worlds. On the one hand, they say, look, it's a local vibration of the field. You say, oh, that's a particle, and you go home happy because they explained the particle to you. And you say, well, how about, how does this influence that over there? Well, see, it's part of the field. It's part of the ocean, extended ocean. And so this fish, which is simply actually a wave of the ocean, not a fish, like a separate entity. It's a vibration of the ocean itself, which is a wave, and this wave affects that wave over there through the ocean, through other waves, I guess. So wave affects wave through the waves. And what are the waves? The waves is the motion of the ocean. That's more or less the notion of a field. That's why they love the word field. So let's look up the word field, and we find some problems here. Here we find that field is a quantity. It's represented by a number that has a value for each point in space and time. And there you see what each one of those words mean. Okay, but essentially a field is just a number. That's it. It's a bunch of numbers. And when they say that the field is vibrating, what they're saying is that the numbers themselves are vibrating. That's what these people are actually saying. So we have a problem because they're not talking physics, they're talking mathematics. And they don't even realize that anymore, because they've always thought of a field as a region where something is happening, and they say there's a something in there, in the field. Whether it's a magnetic field or a gravitational field or electric field, something is in there. But it's that something that they've never identified. And so what they've done is they said, well, we don't care what it is, because a mathematician doesn't care what's in there. He just says, look, we can measure the strength of the field locally in each one of those spaces. And we say, here it's stronger and here it's weaker. That's all they care about. And they say, here it's so many, whatever newtons or whatever, if it's a gravitational field. They can tell you what the strength of the field is at different points in that region. But they cannot identify the invisible, intangible things that are causing that effect. Okay? And so one fellow says here, he sends me a note or a comment, and he says, field is a mathematical representation, regional differences in strength. Exactly, that's all it is. It's a bunch of abstractions. Well, we're talking about a bunch of numbers that are moving, are vibrating. So yeah, it is a mathematical representation. It's just regional differences in strength, and that is not a physical object. What this fellow mentioned here is a concept, and we cannot do physics with abstract concepts. So for all those who try to do that, they are what do we call them? Flatlanders. That's what we call them.